Hi, my name is Pedro Vergara, and today we will talk about what grid congestion is. To understand grid congestion, we have two learning objectives. First, to describe the causes of congestion and its impact on the electricity infrastructure. Second, to compare the different approaches that distribution system operators, DSOs, have available to solve congestion. So first, what is grid congestion? According to RVO, the Netherlands Enterprise Agency, grid congestion happens when at peak moments there is too little spare capacity in the electricity network to transport all the electricity that is being demanded or injected. In those moments, parts of the grid becomes overloaded, meaning the network cannot safely carry the required flows. In practice, you might still see a slightly different definition depending on the context. Additionally, congestion is not only a technical issue. It is both a physical and an administrative problem, and it is also shaped by rules and regulation. In the next slide, we will explore this. We can look congestion from two angles. From a physical perspective, congestion is visible in real time through issues like voltage violations and overloaded assets like cables and transformers running beyond safe limits. From an administrative perspective, congestion shows up over longer time horizons, weeks, months, or even years ahead, when there is no capacity to grant new customers or new generation the access right that they request. This is when you get waiting lists or restricted connection. And to plan well, you also need a good understanding of the physical constraints. As a simple example, consider a neighborhood with many solar panels. On sunny days, the voltage can rise too high. Even if the total energy over the day looks fine, the local peaks can push the network outside its limits, resulting in congestion. What are the causes? There are several layers. Technical causes are the most intuitive: more distributed generation plus higher electric demand from EV charging and electrified heating. The challenge is that our electricity grid was not originally designed for this combination. Then there are administrative causes. Some users hold contracted capacity that they rarely use, while others need it. So capacity exists on paper, but it is not available in practice. And finally, there are regulatory causes. Grid operators often need to be conservative for safety and reliability. And regulation can be slow or inflexible to adapt, which makes reallocating or sharing capacity difficult. What is the impact? Technically, congestion puts stress on equipment. The operation close to limits accelerates asset degradation and increases the need for reinforcement, new cables, transformers, substations. Congestion could also decrease grid reliability if operation near the limits causes equipment to trip more often. Societally, the impact can be significant as well. The limited available capacity can delay connections for businesses and housing projects, require curtailment of renewable generation to relieve stress from the system, and ultimately result higher costs that eventually show up as economic losses and reduce progress on climate goals. How do we solve it? The first is grid reinforcement, building more capacity. This is essential because it solves fundamental shortages and it is the most resilient way to reduce congestion. But reinforcement alone won't be enough for all future use cases. With large amounts of new generations connected in lower grid levels, and with more all-on, all-off demand patterns from electrification, it is not realistic that we can build reinforcement fast enough or affordably enough to always guarantee unlimited capacity everywhere. That's why the second lever is flexibility, changing when and where electricity is consumed or injected, so peaks are reduced and the existing grid is used more efficiently. DSOs can unlock flexibility in multiple ways. direct contracts with customers, network tariffs that encourage off-peak behavior, and market-based approaches like local flexibility platform. Each option has its trade-off, and we will discuss them in the next slide. With direct contracts, the DSO makes one-on-one agreements with users about how capacity is used. For example, they can agree with a customer on a capacity cap. The users set a maximum level of grid use, and in return, they might receive a financial compensation or a discount. This immediately reduces local peaks where the grid is constrained. In the Netherlands, there are already several contract types like such, and more are being developed. This links to connection agreements. Traditionally, users get firm capacity, meaning it is always available. But in congested areas, DSOs can offer non-firm capacity, capacity that is available most of the time but can be curtailed during rare stress moments. Non-firm contracts can help connect more users by using spare capacity but keeping the right to temporarily limit usage when the network is under pressure. Tariff, on the other hand, try to steer behavior through price signals rather than individual contracts. Examples include volumetric tariff, capacity-based tariff, time of use tariff, and in some cases more dynamic designs. The advantage is scalability. One tariff structure can influence thousands of users. The downside is uncertainty in the effect. Tariffs do not guarantee that the user will respond as intended, and if many users respond in the same way, they can even create new peaks. Finally, market approaches aim to procure flexibility where and when it is needed, by letting parties offer and trade flexibility. A Dutch example is GoPax, which coordinates flexibility to help manage congestion. The basic idea is the grid operator signals a local problem, and market parties respond with flexibility bids, so the system can be relieved without always building new infrastructure. In practice, this can be hard. Congestion is highly local, so liquidity can be limited. Sometimes there just aren't enough flexible resources in the right place. And setting up this mechanism is complex. It requires data, coordination, clear products, and trust that the market will actually deliver in critical moments. In this video, we define a grid congestion as the inability to satisfy current or future transport demand because flows would exceed the grid capacity at peak moments. We also highlighted that congestion is more than purely technical grid issue. It has administrative dimension and is shaped by regulation. We then discussed the main drivers: growing distributed generation and electrified demand, capacity lock in contracts, and regulatory constraints, which can stress assets, reduce reliability margins, delay new connections, and lead to curtailment and higher system costs. Finally, we compare how DSOs can respond, reinforcing the grid as the most resilient measure and complementing it with flexibility through direct contract, tariff incentive, and market-based procurement to reduce peaks and make better use of the existing capacity.